Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on theory of numbers, lecture number 4, in which I will discuss Euclidean algorithm to find the GCD of two integers. Now we will discuss about Euclidean algorithm. Statement: let B and C is greater than 0 be two integers B.Sc equal to GCD of integers B and C. We may find GCD of integers B and C with repeated application of division algorithm in series. Here B equal to C Q1 plus R1. Q1 be the quotient when B is divided by C, and R1 be the remainder, and R1 lies between 0 and C. C equal to, next division algorithm, C equal to R1 Q2, Q2 be the quotient and R2 be the remainder when C is divided by R1. Here R1 be the remainder in the first case, and in the second case C is divided by R1 and we get remainder R2. R2 lies between 0 and R1. Next division algorithm, R1 equal to R2 Q3 plus R3. Here Q3 be the quotient when R1 is divided by R2 and R3 be the remainder. R3 lies between 0 and R2. And we proceed this process, we get R j minus 2 equal to R j minus 1 Qj plus Rj. R j minus 1 equal to Rj Q j plus 1, and remainder is 0. According to the Euclidean algorithm, the last non-zero remainder is the GCD of integers B and C. Here last non-zero remainder is Rj. Rj is the GCD of B and C. Also, the GCD of B.Sc is the linear combination of B x naught plus C y naught. X naught and y naught are suitable integers. That is Rj equal to B x naught plus C y naught. Now we prove this. Proof. Since B and C are two integers where C greater than 0, we know that GCD of B and C equal to under bracket BC, and this equal to GCD of C and B, and this equal to C B plus CP. P belong to Z. P is an integer. And by using this formula, we prove the Euclidean algorithm. By using division algorithm, we get quotient Q1 and remainder R1. Putting P equal to minus Q1, we get GCD of B and C equal to C B minus CQ1 and this equal to C R1, because by division algorithm B equal to CQ1 plus R1. R1 be the remainder and Q1 be the quotient. Therefore, B minus CQ1 equal to R1. R1 equal to B minus CQ1. Let this is number 1. And this equal to R1C, means GCD of R1 and C. Here GCD of B and C equal to GCD of C and B. And we may write using this formula. By dividing C by R1, we get quotient Q2. Then we write this equal to R1 C minus R1 Q2. Since C equal to R1 Q2 plus R2, R2 be the remainder by division algorithm. This equal to R1 and here C minus R1 Q2 equal to R2. Implies that R2 equal to C minus R1 Q2. This is number 2. We may write this R2 R1 means GCD of R1 and R2 equal to GCD of R2 and R1. And we proceed this process. We will get this equal to Rj minus 1 Rj means these are all remainder in division process, and this equal to Rj minus 1, and using this concept we will get this Rj 0 and this equal to Rj. Therefore, GCD of B and C will be equal to Rj. This Rj is the last non-zero remainder in division process. So, we prove the first part of the Euclidean algorithm. First part proved. Now we prove the second part. Since in number 1 we see that R1 equal to B plus C under bracket Q1. Therefore, remainder R1 is a linear combination of integers B and C. Let this is number 3. In 2 we get R2 equal to C minus R1 Q2. This equal to C minus putting value of R1 B plus C minus Q1 Q2. This equal to B minus Q2 plus C 1 plus Q1 Q2. This is number 4. Therefore, R2, remainder R2 can be expressed as linear combination of integers B and C. And following this process, we will get that Rj, last non-zero remainder, which is GCD of B and C, may be expressed as linear combination of B and C. We may find the value of x0 and y0 similar to 3 and 4. Therefore, GCD, Rj is the GCD of B and C, is expressed as linear combination of integers B and C. Here x naught and y naught may be obtained. Therefore, proved. Now we solve a problem. Problem is by using Euclidean algorithm and simple calculator, find the greatest common divisor of 42,823 and 6,409. Also find integers x and y satisfying the equation 42,823x plus 6,409y equal to 17. Now we solve this by using Euclidean algorithm. Since in Euclidean algorithm, the application of repeated division algorithm is used to find the GCD of two integers. Here, by division algorithm, we may find 42,823 equal to, when this number is divided by this number 6,409, we get the quotient 6. So we write here 6,409 multiply 6 plus remainder is 4,369. So, by Euclidean algorithm, we write the GCD of 42,823 and 6,409 equal to, we get here remainder 4,369 and here 6,409 and here 4,369. Again we repeat the division algorithm. Here we write 6,409 equal to, if we divide this by 4,369 means remainder, first remainder, we get quotient 1. So quotient will be 1. We write here 4,369 and remainder will be 2,040. Here we may write this GCD equal to 4,369 and 2,040. Again we repeat the division algorithm. Here we write 4,369 equal to, if we divide 4,369 by 2,040, we get quotient 2. So we write quotient 2 here 2,040 and remainder is 289. So this will be equal to the GCD of 2,040 and 289. Again we repeat the division algorithm. by writing here 2040. If we divide 2040 by the remainder 289, we get the quotient 7. So we write here 7, here 289, and remainder will be 17. Therefore, this will be equal to GCD of 289 and 17. Again, we repeat the division algorithm by writing here 289 equal to, if we divide this 289 by 17, we get 17. So quotient is 17 and remainder is also 17, and last remainder, here remainder is 0. So we get remainder 0. Hence, according to Euclidean algorithm, the last non-zero remainder is 17. Therefore, GCD equal to last non-zero remainder 17, and this will be 17. We may solve this problem in short form by making a table. Firstly, write here quotient. Qi plus 1. Then remainder. Ri. Then xi, and here yi. Here we first write 42,823. Here we write 1, here 0, because here 42,823 equal to 1 multiply, means x multiply by 42,823 plus 0 multiply 6,409, and this equal to 42,823. Second, we may write here 6,409. This will be equal to here 0, here 1. So this means 0 multiply 42,823 plus second place 1 multiply 6,409. If we divide 42,823 by 6,409, we get quotient 6. Now, multiplying this line by 6 and then subtracting from this line. So, here we will get 4,369. If we multiply 6,409 by 6 and we subtract this from 42,823, we get 4,369. Then we multiply 0 with 6, we get 0, and we subtract this from this 1. So we get here 1. Now we multiply 6 by 1. We get 6. And if we subtract this from this 0, we get here minus 6. Now we divide 6409 by 4369. We get quotient 1. Now multiplying this line by 1, then subtracting from this line, here we get, if we multiply 1 with 4369 and we subtract this from 6409, we will get 2040. Now we multiply 1 by 1, we get 1, and we subtract this from 0, we get minus 1. If we multiply 1 with minus 6, we get minus 6. Now we subtract minus 6 from 1, we get 7. Now we divide 4369 by 2040. We get quotient 2. Now multiplying this line by 2 and then subtracting from this line. Here 2 multiply by 2040 and then subtract from 4369. We get 289. We multiply 2 with minus 1. We get minus 2. And we subtract it from 1. 1 minus minus 2. This equal to 3. We multiply 2 with 7. 14. Then subtract this from minus 6. And here will be minus 20. Now we divide 2040 by 289. We get quotient 7. Now we multiply 7 with 289 and subtract from this. We get 17. Now we multiply 7 with 3. 21. Then we subtract 21 from minus 1. We get minus 22. Now we multiply 7 with minus 20. We get minus 140. Then we subtract minus 140 from 7. We get 147. Now dividing 289 by 17, we get quotient 17 and remainder 0. Therefore, we get here exact divisible. So, the last non-zero remainder will be 17. Therefore, GCD of 42,823 and 6,409 is 17. Here we get the value of x naught equal to minus 22 and value of y naught is 147. Therefore, we may write 17 equal to 42,823 multiply minus 22 plus 6409 multiply 147. Here x naught equal to minus 22 and y naught equal to 147. That is, our value of x is minus 22 and value of y is 147 for this equation. Therefore, we solve this problem. Now, I will give you details of my lecture notes. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and to subscribe my YouTube channel. Thank you.